this is certainly my focus of my research more, because I think in the future we hear much about how to treat patients, and we certainly only have the first generation of pharmacological treatment strategies with 3 cholinergic drugs and 1 memantine working more on the glutamate system, you could say. Those drugs have some effect. They are really the first generation, and the last one was approved in Europe in 2002, so it's like soon 20 years ago. And that is memantine. It was a drug from a German company called I don't remember. Merz Pharma in Frankfurt. Merz Pharmaceuticals. So that was a fantastic thing at that time. But since then, some 100 trials have failed actually, and we are lacking 2 things. One is that we must be more precise in our diagnosis. And today, with the diagnosis based on biomarkers that reflect what is happening in the brain, either via more extensive imaging investigation, magnetic resonance, positron emission tomography, or via the cerebrospinal fluid taps, we can really, with the biomarkers, outline more homogeneous groups that we could include in clinical trials. And these trials are certainly then based on molecules that researchers have found of interest due to the mechanism they think are causing the too early nerve cell deaths in this disorder, in Alzheimer's disease. The prevailing ideas or hypotheses have certainly been the focus on beta amyloid and also on tau. Those were the histopathological hallmarks that Alois Alzheimer already in 1906 described in his speech to the German Association of Psychiatrists at that time. And I must say the beta amyloid, my belief is certainly that beta amyloid is of great importance. That's for sure. But due to the failures of the trials, it's probably true that we have to add some other treatments. And this more cocktail approach we use in many other disorders like cardiac insufficiency, in diabetes, in cancer treatment. You combine different treatment strategies. So I think that's very natural for us. And so perhaps if you can combine an approach against beta amyloid and against tau and against inflammation and against something else, it will be, of course, more effective. There are problems involved in that. We have also heard about non-pharmacological treatment strategies, but my focus is certainly on the pharmacological side to look on the targets. And upcoming targets are, for example, inflammation. I mentioned inflammation. And that was actually mentioned already by Alois Alzheimer, that in the brains that he brought to autopsy, the plaques and the tangles were surrounded by inflammatory cells, glial cells or astrocytes. So that's nothing new. Other targets are the nerve cells themselves. How can we save the nerve cells? How can we have a neuroprotection? That's certainly a target if we can add, for example, some of these growth factors. We have heard about nerve growth factor or brain-derived growth factors, or today we also speak a lot about gene therapy. You can bring in genes. We from the I told you about the COVID and Alzheimer's, about the ApoE4 individuals have some increased risk, and one approach now is even to bring in some of the good ApoE2 or 3 into the brain on a patient that has the ApoE4, that is a risk gene involved in the disease. So these are very preliminary studies, but they then put via a virus vector E2 on top of the brain in the subarachnoidal space. They put it into the cerebrospinal fluid and it surrounds the brain, and they hope that this E4 driven proteomics will then be replaced by some E2 driven, a good guy instead of a bad guy, so to say. So gene therapy is coming, but we are not really as a target seeing this strategy. Others speak about autophagy. You know, there was a Nobel Prize also for autophagy. There was one for nerve growth factor that this Italian researcher Rita Montalcini got. Autophagy is the process is to clean the brain of waste. And so if the autophagy is not functioning, we could say, well, we got more waste into the brain, and that leads to the disorder on effect on cognition. Other people look on the structures in the brain, and we know that these nerve endings, not the nerve cells itself, but they have 10,000 of connections, dendrites and nerve endings, and they are very energy dependent. So if you can in some way influence the energy there, and the atomic energy supply is done by the mitochondria, and the mitochondria produce the ATP. So if you can save the mitochondria in the disorder, that's a good approach. And we know that the metabolism is deranged in the patients. We can, for example, by using this positron emission tomography and looking on fluorodeoxyglucose, you can see that you have a decrease in the glucose metabolism in some specific areas when we put the diagnosis. Other possibilities are certainly brought by the basic research. And I mean that if we should find some pharmacological treatment for this new, we have to intensify the basic research. And I say that as a clinician, but I really mean it. And we have to bring in people who understand basic research, molecular biologists, geneticists, mathematicians, whatever you find out there in the pubs. You may not go to the pubs, but we may. So we are searching for researchers in this field. And what we have been doing here in our groups we have been focusing on one peptide that inhibits the aggregation of these abnormal proteins. It's called BRICOS. And another approach has been to really stimulate the mitochondria to increase the membrane potential and increase the ATP production. And that molecule we call GMP1, and then I talked a bit about that sometime earlier. And the latest approach we have taken is what you will ask me about later. It's called FKBP51 HSP90. It's an interaction between, we could say, two proteins, and we'll come back to that. But anyhow, I think there are much research. We need more basic research to understand the mechanism before we can really design the best studies. And this takes time, and people have to understand it takes time. I don't dare to say we have a treatment in 3 or 5 years anymore. I said that 30 years ago. No, I don't want to say it again. This is really The other hallmark that Alzheimer described, as I said, was the tau. That's an intracellular change where tau is phosphorylated and aggregated and causing these neurofibrillary tangles inside the nerve cells. And when this change occurs, the transportation of important molecules down to the synapse is hindered in a way. So you can understand when it comes in many dendrites or nerve cell outgrowths, it stops a bit of the energy or the supply needed in the brain. And much was here done with earlier with inhibitors of one of these, we call it chaperone-co-chaperone interaction. It's called HSP90. And HSP90 has been to have inhibitors of HSP90 would give a good effect, but that treatment approach had so many side effects. So it's important in all cells, not only the nerve cells. So now what we have focused on is to, in some way, intervene in the interaction between this FKBP51 and HSP90. So that's to inhibit this interaction is our approach without having so much of side effects. And we call that a protein-protein interaction inhibition. So by that approach, to developing molecule for that interaction between these two peptides, then we can decrease free tau in the brain, and we decrease the levels of phosphotau, which is causing the aggregation, and actually getting more tau free for degradation that is transported out of the brain. So that is our idea, and we have now preliminarily developed some molecules with different tests that we are now trying to passing all barriers. They have to be taken as a small molecule per os. They have to be cheap, not like the immunotherapy, taken up in the gastrointestinal tract and passing the blood-brain barrier, and hopefully also passing inside the nerve cells. That's another barrier that is difficult to pass. So the preliminary results we have is that we could decrease tau levels in our cell models. And from that now we are going over to in vivo models. We make flies, Drosophila flies, transgenic for Alzheimer's disease, and then we test it, adding it to the food that the flies are eating. The next step is we have transgenic mice models for Alzheimer's, and these models should then also have senile plaques and tangles. And we will then study the tangle formation, and we can of course then in the same time do behavioral tests. The flies, if they can fly, climb the wall, if they survive as long as the wild type flies, if they have assembled amyloid or tau to the same degree as the wild type flies, or hopefully less than when we treat them. So and then with the mice, we can also do a lot of neuropsychological testing. They can swim in swim mazes, or they can find, they are afraid of coming on open arms. If you test on an arm test, they want to keep more in the hidden space, we could say. So there are different neuropsychological tests. And we are also developing a transgenic rat now that the rat is much closer to the human being. And so a rat model would be the ultimate animal model before moving into toxicology and then moving into phase 1, phase 2, phase 3 trials. So drug discovery, you have to survive and persevere. I will not, I will hopefully see a good drug, but I cannot promise you anything. There are many companies who think they have the trick to do, but I'm not sure they are right yet. You have to understand the basic mechanism first.